Welcome to today's statistics tutorial. Today we will be looking at linear regression and correlation. See the links below for the calculators and resources used in this tutorial, as well as additional supports and resources to help you with your statistics course.
Module 12, which is on linear regression and correlation. So linear regression for two variables is based on a linear equation with one independent, which would be your x values, and your y values, which would be your dependent variable, and your a and b are constants. So for statistics, the formula is y equals a plus bx. So this is for statistics, and you'll notice it looks very much like the y equals mx plus b formula that we use in algebra, which is the equation for a line. And these two are exactly the same. They're just written differently, and that helps to identify, are you talking about something with statistics, or are you talking about something for algebra? So your A from the statistic equation and your B from your algebra equation is your y-intercept, or where your which is the value when x equals 0, and it's where it crosses the line. And I did not give you the whiteboard link yet, so let me do that. And then your b of x on the statistics formula is the exact same thing as your mx on your algebra formula, and your b is going to equal your m, which equals your slope, which just determines the steepness of the line. Okay, when you have your data, so when you have your data, you're going to have your x and your y. So it's just like what we've seen before with algebra. And then you're going to have scatter points. And these are all going to have an x and a y. For each of these points, it's going to have an x and a y value, where x is going to be your independent. So that's what you choose independently. And then y is considered dependent because you plug in for whatever value of x you have, you're going to plug it into the equation to solve for y. Then with your data, you're going to plot your data on what is called a scatter plot, which we've seen before, and that just says you're going to put the points on a graph and see what it looks like. So if I have something that looks like this, this is going to be something that looks pretty close to a straight line, so that would be considered a strong positive linear pattern. If I had one that looked similar and then there was a point out here, that would be a strong positive linear pattern with one deviation, because there's one that's a little away from the what looks like a straight line. If I had where they're all kind of spaced out big, but still kind of forming a line, this would be considered a weak correlation. And so this would be, because it's going to the right, anytime you're going to the right, it's going to be considered positive. If I'm going the other direction, let's see, it's like something like this. This right here would be considered a strong negative linear pattern. So if it's going to go to the left, it's going to be considered negative. If it's going to the right, it's going to be considered positive. If I have one that's kind of staying on the bottom and then slowly comes up, this is going to be an exponential growth pattern. and that is not one that's going to fit this line because it's a curve. And if we have one where our data points are just kind of all over the place, that would be considered to have no pattern. On our line, if we have, so if I have a line going to the right, that is considered positive correlation. And that means that the signs of my slope are going to be the same. They're either both going to be positive or they're both going to be negative. And that's going to be considered a positive correlation. If it goes the opposite direction, that's considered a negative correlation. And that just means that signs of my y and my x are going to be opposite when I'm looking at my slope. So this is going to have a negative slope, which means it's going to go to the left. And when I'm doing my solving for my y or my x's, they're going to be opposite. If it's a horizontal line, that's going to be considered a zero correlation or no correlation. And when we're solving these linear regressions, if the line has a curve to it, like we saw with this exponential growth, then it might also show up as having no correlation or zero correlation because it doesn't fit into a straight line. If I have a vertical line, that's considered undefined. So, and that's because when we're doing the straight line. So anyway, so that is considered undefined, so you won't see that showing up at all. Now, if data has a linear relationship, we can use linear regression to draw a line that represents our relationship, given that one variable explains the other, or for a given x, we can use the regression line to predict y. So that's why we would want to use this, is that we can get two sets of values and let one be dependent on the other if it looks like the data is going to have close to a linear or a straight line, then we can use it to predict possible outcomes, possible values. So if we have a set of data points that appear to fit a straight line, then this is called a line of best fit or least squares line. So if I have all of this data here, and this kind of looks like it's going to be a straight line, so I can draw a straight line to represent all of these data points, even though I've got some that are a little above, some that it is below. And this is called the line of best fit or the least squares line. And we get this so the way that we get this, and the Khan Academy has a really good video explaining these values. So the equation for this line, and we're going to do an example here pretty soon, is going to be y hat, or which is an estimated y, equals a plus bx. And we get this y hat, we calculate this, so this point, let's say this point here, that's going to be like y1, x1. Then this point, this difference between where that point is and where that line is going to be the difference between y1 and y hat. And we can calculate all the errors, and we'll go into this more, but this is called, when I sum, this is called an epsilon, and I get my where is it? The sum, so the sum of the squared errors is going to be the summation of all of these y's minus the estimated. So it's going to be these points minus the point on the line squared summed, and that's going to be kind of all of the errors. And this line, this best fit line, is going to want to minimize that error as much as possible. So that's just really brief explanation. And we'll go into that more detail on how all of this equation can be, how this equation is derived. You can go to the Khan Academy of Statistics videos, and they have some videos on line regression, and they will go through all the steps of how that line is calculated. But in order for you to solve the problems with your assignment, you don't need to know that process. So I'm going to just go ahead and skip that part, and you can look at that if you want. So let's go ahead and do an example. So if we have a random sample of 11 statistics students produce the following data, where X is the third exam score out of 80, and Y is the final exam score out of 200. We want to know, can you predict the final exam score of a random student if you know the third exam score? So let's write down what do we know. We have N is going to equal 11 students, and then we've got our X's and Y's. So in order to solve this, we're going to need to use a regression calculator. So from my data, I'm going to go ahead and put in my values. And with this, you just need to have a space in between each of these numbers. So I've got 65, 67, 71, 71, 66, 75, 67, 70, 71, 69, 69. And then I'm also going to do the Y values, 175, 133, 185, 163, 126, 198, 153, 163, 159, 151, 159. Okay, so our X values are the third exam score, and then our Y values are the final exam score. And then we're going to use this calculator to find the equation of the regression line. And then I'm also going to click here. With this calculator, you can also show an explanation. So this online calculator is going to show me all my data. It's going to give me the equation of the regression line, and it's also going to graph it. So this straight line, so it's graphed all of my points, and then it's also going to give me the straight line, which is this best fit line. And then here, it's also going to show me how all of this was figured out, just so that you can see where did this information come from. Okay, so using our calculator, we were able to calculate that our equation, the best fit line is a minus 173.513 plus 4.827x. So the equation for the best fit line is y, and this is actually y hat, is a plus bx, and that's where a equals the mean of y minus b times the mean of x. B is going to equal the summation of x minus the mean of x times y minus the mean of y, all divided by the summation of x minus the mean of x quantity squared. And the best fit line is always going to pass through the point, it's always going to pass through the point of the mean of x and the mean of y. Another way that you can write the slope can also be written in the form of r, which is the correlation coefficient, which we'll look at next, times the standard deviation of y divided by the standard deviation of x. And it's important to know what these formulas are, but you're going to use your calculators in order to solve it. And if you had the T184 calculator and you plugged that in, I'll show you what that looks like. And the book, if you have that calculator, the book will walk you through the steps of how to use that calculator. But you can see from this screen that it gives us, once again, it gives us the equation for y, and it will give you your, let's see, so your, in addition to your equation, where is it, right here? So it's going to give you your A and your B, which you can see the calculator, we got real similar results. This one is also going to give you S, which is your standard deviation, and it's going to give you your R, which is your correlation coefficient. And you can calculate these numbers in other ways, but I wanted you also to be able to see what it looks like on the calculator. And if you that software, the link that I sent you guys last time, the Texas Instrument, you can download that software for this calculator and get a free 90-day trial. So for some of this latter stuff, if you haven't already done that and you don't have the T184 calculator, you might want to do that, just because I'm seeing some variability as far as calculating things by hand versus what's showing up with the calculator. Okay, so we use our online regression calculator to get our equation based on our data, to get our equation for the line, and that will solve for our A and our B values. So this is my A, and this is B. So remember that the formula is the y equals A plus BX. Okay. So the way that we would interpret this, so the B, our slope B, tells us how y changes for every x, every 1x. So for this particular exam, we got a B. Our B is going to be equaling to 4.827, which we could round to being 4.83. And that all that's saying is for a 1-point increase on the third exam, which is our x values, then we would expect the final exam, the points to increase by 4.83 on average. Now, the process of fitting the best fit line is called linear regression. It's based on the assumption that data is scattered about a straight line. The best fit line is the line where the sum of the squared errors is minimized. And that's what I was showing before, where the distance between the data points and the line, you want those to be as small as possible. The best fit line is called the least squares regression line. And that's just, if we look at, let's go back. So if we look at our calculator, so this line right here, that is called your best fit line. It is also called the least squares regression line. And the sum of the squared errors is the sum of the squared distance between the actual data point and the line of best fit. So that's what we talked about right through here. This line, this distance between these 2 points squared and added together is going to get your sum of the squared errors. So now the next thing that we need to calculate is we want to calculate this R, which is the correlation coefficient, because that tells us, that provides a measure of the strength and direction of the linear association between the independent X values and the dependent Y values. Okay, and this is also something that our online calculator will calculate. So the formula for R is going to be N, which is the number of data points that we have, times the summation of X times Y minus the summation of X times the summation of Y, all divided by the square root of N summation X squared minus summation of X squared times N summation Y squared minus the summation Y quantity squared. Now R, okay, so let's go ahead and go back to our calculator. So this same calculator will also, so it saved all of our data points. So once we get our equation of the line, then we can go and switch it to find the correlation coefficient. So once again, it's going to show us our data. It's going to give us our correlation coefficient, and it's going to also show how everything was calculated. And you can keep this second half of showing the steps if you want, or you can do it. You can still do the calculation without that. Okay, so this is giving us a correlation coefficient of 0.6631 for our data using these 2 exams. So the few things about R is always going to be between -1 and a +1. So if R is close, the closer the R is to either a -1 or a -1, then that's going to show a stronger relationship. If it's going close to a 1, if R equals 1, that's a perfect positive correlation. If R equals a -1, that's a perfect negative correlation. If R equals 0, there's no correlation. So the stronger to plus or minus. So if I'm on a graph and here is 0, here's 1, here's -1, this is going to be no 0 relationship. So 0 relationship to this is going to be real strong. And this is going to be, so when it gets close to the 1 or the -1, it's going to be real strong. And a positive, this means it's going to go to the right. Negative means it's going to go to the left, and that's the slope of the line. And the sign of whatever the coefficient is that's always going to be the same sign as your slope. So if I have a negative R, we're going to also have a negative B, or a negative slope and a negative correlation. So now we have the coefficient determination, which is your R squared, is usually expressed as a percentage. So the percentage, and it's the percentage of variation in Y that can be explained by variation in X using the best fit line. And 1 minus R squared, so this is this is going to be like it can be explained, and then the 1 minus R squared is also going to be listed as a percentage, and it's the variation not explained, or it's the scattering of the observed points. So for this particular problem, if I have an R of 0.6631, then my R squared, I'm going to square that, and that's going to give me a calculation of 0.43970016. So that means as a percentage, my R squared is going to be about 44%. My 1 minus R squared is going to give me, I'm just going to take 1 minus that number, and that's going to give me a 0.560298. So that means, once again, I'm going to say this as a percentage. So this is going to give me my R squared is going to be about 56%. And then if you'll notice on the calculator results, it gave you both R, which was the correlation coefficient, and the R squared, which is your coefficient of determination. And then the way that we interpret this is we say approximately, so for this particular set of data, we would say approximately 44% of the variation in the final exam grades can be explained by the variation in the grades on the third exam using the best fit regression line. Therefore, approximately 56%, which is our 1 minus R squared, 56% of the variation in the final exam grades cannot be explained by the variation in the grades on the third exam using the best fit regression line. And so that is how this explains the point scattering on our data, which we saw before. Okay. Any questions so far? Okay. The next thing we want to do is we want to test the significance of the correlation coefficient to determine how strong or weak or whether or not there's a correlation. And with that, we're going to use a hypothesis test to determine if the sample linear relationship is strong enough to model the population linear relationship. So far we've just been working with the sample. Now we want to do a test to determine is there a strong enough correlation to say that this applies beyond the sample to the population. So the way that we're going to do that is we're going to use the hypothesis testing that we've seen before. And what that is our null hypothesis is we're going to hypothesize that the population correlation coefficient, which is rho, is not significantly different from 0, which means there is not a significant linear relationship correlation between x and y in the population, and we cannot use the regression line to model a linear relationship between x and y in the population. And we're going to put our alternative hypothesis to say that rho does not equal 0. And that just says that the population correlation coefficient is significantly different from 0, which says there is a significant linear relationship or correlation between x and y in the population. Therefore, we can use the regression line to model the linear relationship between x and y in the population. So we're going to continue using the same sample data with the test. And there's two ways that you can test this hypothesis. The first one is using the p-value method that's similar to what we've done before, and or the second method is using a table of critical values. So if our significance level is greater than the p-value, then we're going to reject the null hypothesis. So this is the same as what we've done before, is if the level of significance was greater than our p-value, then we're going to reject the null hypothesis and say that the evidence supports the alternative. So this would be the conclusion would be there is sufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is significantly different from 0. Now, if the p-value is greater, so if the p-value, if the level of significance is less than the p-value, or which we could write it either way. So if the level of significance is not greater, which means that it's less, then it means that we're not going to reject. Do not reject the null hypothesis. And that means that there is insufficient evidence to conclude that there is a significant linear relationship between x and y because the correlation coefficient is not significantly different from 0. Now, in order to do this, we are going to use the t-distribution. We're going to use our t-distribution calculator. With degrees of freedom, with our degrees of freedom equaling n minus 2. And it's going to be n minus 2 instead of n minus 1 because we have two variables. The test statistic that we're going to use So our test statistic is going to have the formula of T equals R square root of n minus 2 divided by the square root of 1 minus R squared. And the p-value is going to be equal the area of the two tails. So let's take a look at, we're going to continue on with the same sample. So let's solve for, that tells us that my degrees of freedom for this particular problem is going to be 11 minus 2, which is going to equal 9. To get my test statistic, I've got my R, which is going to be 0.6631. Then I'm going to do the square root of n minus 2, which is 9. And then I'm going to divide it by the square root of 1 minus R squared. So that is going to be the square root of 0.560298. And then when I do that calculation, I end up with a t-score of 2.657601, which we will just round off to be 2.658. Okay, so now I'm going to want to find my p-value of where x is greater than my t statistic, which is 2.658. So I'm going to plug that into the t distribution calculator, which we've used before. So we're doing the t distribution with 9 degrees of freedom, and the probability that x is going to be greater than 2.658. Okay, so that gave me a value of, let's scoot this over so you can see it, 0.13066. Now you want to remember this is a two-tailed test because we're using the equal sign. So this is going to be half of my p-value. So in order to get my p-value, I'm going to take this number, multiply it by 2, and that's going to give me a p-value of 0.026132. Okay? So now our critical value is going to be 0.05 because it wasn't stated. So we always assume if it's not directly given, then it's going to be 5%. So now we're going to look at our rules. We're going to have our 0.05 and 0.0261. The 0.05 is greater, so our alpha is greater than our p-value. So that tells us we're going to reject the null hypothesis. So that tells us that our conclusion is there's sufficient evidence to conclude that there is a significant linear relationship between the third exam score, which are your X's, and the final exam score Y, because the correlation coefficient is significantly different from 0. And because R is significant and the scatter plots show a linear trend, that tells us the regression line can be used to predict the final exam scores. Okay, any questions so far? Okay, now the second way that we can do that is using, so this is testing this out using the p-values. The other way that we can do that is to use a table of critical values. Okay, so what you're going to do, the way that you look at this is you want to go to you're going to find your degrees of freedom. So in this case, our degrees of freedom here is 9, and you're going to match it with the critical values. So this is giving us a critical value of 0.062. So basically what they're doing is they're going to give you a line here. So here's 0, and they're going to give you a range. This is for 9, it's 0.602, which means the other end is a minus 0.602. So these are your critical values. And if our R value is between these two values, then it's not significant. If it's outside, if it's either greater than or less than, then it's going to be considered significant. So then we want to go and look, and our R value was 0.6631. So that means that's going to be, we'll say, about here. So we have 0.6631 is our R value. So because that R value is greater than 0.062, it's greater than, then that means that R is significant. So 0.6631 is greater than 0.62, so that tells us that R is significant. And that means we can reject the null hypothesis. Okay. Any questions about how to use the table to determine whether or not R is significant and whether or not you should reject the null hypothesis? Okay. Any questions about anything we've gone over so far? Okay. So I'm going to get a new whiteboard, and then we'll move on to prediction and outliers. Okay, so now we're going to look at prediction. So because we've identified that R is significant, we can now use the least squares regression line for prediction. So let's go ahead and write what our equation is. Let's write that down again. So the equation that we got for our least squares, our least squares regression line was the estimated y equals a minus 173.51 plus 4.83x. So now when we've got, so now we want to use it for prediction. We've proved everything so now that tells us we can use this line for prediction. So suppose we wanted to estimate or predict the mean final exam score of the students who received a 73 on the third exam. So that would be, let's say somebody got a 73 on the third exam. Now, because our values range between 65 and 75, then that tells us that we can substitute in X for, we can substitute in the value of X equaling 73 and solve for Y to get our final expected score. So then all I'm going to do is I'm going to take my equation and plug in, instead of X, I'm going to plug in that 73. And that's going to give me a value of 179.08. Okay, so what that would tell me is that we predict that students, any of the students who score a 73 on the third exam, we're going to predict that they will, on average, that they will earn a score of 179.08 on the final exam. And the process of predicting inside the observed data of X values is called interpolation. The process of predicting outside of the observed X values is called extrapolation. So on this, when we were dealing with our X values, we were dealing with scores between 65 to 75. So that means that anything in between, any X values that are between 65 and 75, so in this case we were looking at 73, then we can have, we can reliably say that we can reliably predict what the final score is for any of these values, so for any value of X between 65 and 75. Now, let's say that I want to predict something that's outside of this range of data values. So let's say I wanted to find out for a student that had a score of 90, what is the likelihood, what is likely to be their final score? So this one, we're going to do the same thing. So let's say X equals 90. Then we're going to do the same thing, plug that in. And that's going to give me a score of 261.19. So we're able to plug it into the formula. However, the largest final score possible is 200. So what that tells us is anything that's outside of the range of our outside of the sample domain cannot be used to predict reliable outcomes. So we can still plug them into the formula, but as you can see, all this is going to tell us is that they'll probably score high, but we can't predict what type of score that student is actually going to get because it's outside of the range that we actually measured. Okay. The last section that we're going to look at is the outliers. And the outliers are when we have our data. So let's see if we've got, if it will show us the graph again. There we go. So here we have the graph. So the outliers, when we're looking at this, outliers are just the ones that are considered further away from the line. And if we have an outlier can be because we've got an error in the data, and that is throwing all of our information off. Or it could be something that's really something that's important, and it's influencing and having a big effect on the slope of the line. So anytime we have an outlier, then that just means that's a point that we need to go and look at it, double check that data. So any point that is considered plus or minus 2 standard deviations from the line is considered an outlier. So we can do that graphically. So let's say we have this. So we've got our main line, and we have all our points. So graphically, we could do it, make a parallel line above and below. That's 2 standard deviations. And then just look at anything that's above or below those lines would be considered outliers. Okay? So we're going to use this sample again, and the standard deviation. So if you use the calculator, it's going to calculate the standard deviations for you. So let me pull that up again and show you where that is. Okay. So if you are using the calculator, then this S value, where it says 16.41237711, that is your sample standard deviation. If you're not using that calculator, then you can do it by hand. Okay, so S is the sample standard deviation of all of the epsilons, or all of the summation of the Y minus Y estimate. So what it's doing is it's summing all of the differences between the points, the data point, and the straight line. So N is going to be our total data point. And let's go ahead and write down some equations. So we've got N is our total data point. So we've got 11. And then our formula for our sample for the sum of the squared errors is going to be the sum of our epsilon squared, which is just the summation of the squared differences between the data point and the line squared. And then the formula for our standard deviation is going to be the square root of our sum of the sample errors divided by N minus 2. And once again, we're doing N minus 2 because we have 2 variables. And then if you'll remember, so this is the same as doing the square root of the summation of the data point minus the Y from the line, minus the line squared. So this is the distance, or the error, between the data point and the line squared divided by N minus 2. And then if you'll recall from Module 2, just to see how this looks familiar, the sample standard deviation for Module 2, when we did it, that was just the value of X minus the mean of X quantity squared divided by N minus 1. So if you're working just with one value instead of 2 values, you're going to use this equation for your sample standard deviation. If you're using 2 values, you're going to use this top one in blue. Okay, so now, so from this one, the calculator gave us a sample standard deviation, let's do it in the same color, of about 16.4. So now, if you don't have that calculator, then you will need to do it by hand. So let's go ahead and do that. So this table did a bunch of the math already for us. So this is showing these are our X values, these are the Y values. This is the estimated doing our equation of the line. It plugs that in for Y, and then it took the differences of those two Y's and gave us the differences. So any questions on how any of this data was calculated? Okay, and so remember your Y equation is just your A plus BX that we solved earlier. So now we've got the epsilon. So in order to get my S sum of the squared errors, then I'm going to take each of these values, each of these differences, and I'm going to square them. I'm going to square them and sum them. So I've got 35 squared plus a minus 17 squared plus 16 squared plus minus 6 squared plus a minus 19 squared plus 9 squared plus 3 squared plus minus 1 squared plus minus 10 squared plus minus 9 squared plus minus 1 squared. So then when I square all of those and add them up, that's going to give me a sum of squared errors equal 2440. We've already established that my n is going to equal 11. So to get my standard deviation, I'm going to take the square root of 2440 divided by 11 minus 2. And that's going to give me 16.46552. So if you'll notice, these two numbers from the calculator and working it by hand are a little bit different. And honestly, I don't know why. And in the book, I used the OpenStat book to get this example, and they showed it with both, and they're slightly different. So this is another thing where when you're doing your assignments and your test exam, if you think you did it correctly, but you get it marked wrong, then make sure you submit your work to your instructor, because it might just be it might be that you've done all of the calculations correctly, but it's just a difference in what type of calculator you use to do your computation that is making your answer slightly different. Okay, so now the next thing, now that we have our standard deviation, we're going to multiply that by 2 to get 2 standard deviations away. So 2 times f is going to be 2 times 16.4, which equals 32.8. So now I'm looking for any score that is going to be plus or minus 32.8. So now we look at all of these scores, and we can see this first one is bigger than 32.8, but everything else, so we're going to look here. So this is 0, so we want minus 32.8 and plus 32.8. And we've got a value of 35 on this first exam. So that tells us that the first student has a residual of 35, and residual is just the term for the difference between the data point and the line. It's referred as epsilon. It's also referred as a residual. So that would be considered, so that tells us this point right here. So that tells us that point 65, which is our x value, and 175 is considered an outlier because it is more than 2 standard deviations. It is more than 2 standard deviations away from the line. And sometimes you can visually see it on a graph, but sometimes, so like say this point right here where it's just barely above that line, that might be kind of hard to visually see it, but your calculations will identify it. So if you have an outlier, then that just tells you that's the data point, you need to take a look at it. If it's an error, then either you need to correct the error or you just need to delete it from your data and recalculate without that data point. If the outlier is not an error, then you want to make sure that you leave it in the data set and see what it tells you about how it's changing the line. And you can also take it out and do your calculations and compare it with and without so that you can see how is that outlier affecting your best fit line or any of your other data. So just for theory, let's suppose that our point 665, 175 is an error. Then we're going to delete the data point and recalculate it. So if we recalculate it, we put it back into our calculation. So let's look at what we had. So that would give me, so without the outlier, then I would get a new line of minus 355.19 plus 7.39x and a correlation coefficient of 0.921. And then what we had originally, just so we can compare it, we had a minus 173.513 plus 4.827x with a correlation coefficient of 0.6631. So when we compare this two data, we look at, by taking the outlier out, we actually got a stronger correlation coefficient because R is now much closer to 1. And this also tells us that this line will better predict the final exam scores given the third exam score. For outliers, when you're comparing your standard deviation, so you want to remember if you've got 2 data points, you're going to use the sum of the errors divided by n minus 2 because you've got two variables. If you're just being given one set of data points, then you're going to use the sample standard deviation formula using the means, and you're going to minus 1 because you just have one variable. But everything else should be basically the same. Okay, so that's everything for this week's modules. Any questions?
I hope you have found this helpful. See the links below for additional supports and resources, and be sure to like and subscribe to get the latest videos from Caz Academy. I'll see you at the next video for more statistics and probability.